here. So today I will just present to you something about nuts. As you can see, it's a very, very broad spectrum, but I will do it in a mixture of giving you some information and explaining this or illustrating this with simple.
Can you
text. Oh yes, sorry. With simple and illustrating this with simple experiments. And you can see here, so from the sailing boats, these are macroscopic knots, down to the level of the cell where DNA makes knots. So it's easy to find knots. There are everywhere. So in sailing, fishing, climbing, surgery, also very important. They are made on strings, fabrics, knits, DNA, ties, shoestrings, and you can add whatever you want. Each time you have a string, something like this, then you will have knots. And who is interested in doing studying knots? Well, math, physics, chemistry, biology, and also material science, because knot influences the material property. Just think at a simple fabric. This is just knotted strings, and how you knit them or how you make these fabrics will influence the material properties. You can do some knits which are very elastic, some which are more rigid by choosing the type of knot. And also with the coming, for example, carbon materials, carbon fibers, knots play a role into the material properties, the resistance to traction of materials, and so on and so forth. I just show you a short outline, some definition, one mathematical property that I will illustrate, then some physical properties of knot, and then knots in biology. Please look at my page number. So if you want to refer to a page, you have to remember which type of knot. Since there are almost infinite numbers, so my talk can go on and on forever. So let's just start with sailing boats, with macroscopic knot that you know. You have this very, very well-known book, and when you look at here more closely, it tells you that there are 3,900 knots inside with 7,000 drawings. And so you can see the wealth of knots, and the wealth of knot comes from the fact that, for example, on sailing boats, you have knots for every very specific application. You want to attach this sail, then you do this knot. You want to attach that sail, you do that knot. You want to make a carpet, then you do some kind of braiding, and you make a knot with this, and so on and so forth. So knots were actually, in my opinion, the advanced materials at this time here. This boat is made out of wood and of some fabrics for the sail, and then strings, just the ropes that make up the rest of the boat. Nowadays you will have carbon fibers, metals, whatever, all kind of advanced material, but at that time knots were playing a very important role.
I walked up the Cam yesterday, and there the boats are not sailing, but they have to park very close, and so there are large bumpers on the front and back which are made from very high crossing member knots, probably beyond the ones you'll have.
Okay.
Thousands of crossings.
Thousands of crossings, okay. And so today we will speak about open and closed knot. These are the knot like the mathematician likes, where the topology is defined, and these are knots like we know when we use them in our daily life, and how to do some, and the knots that we encounter when we want to do physics. So knot science started with Thomson, and he and Maxwell thought that the stability of atoms and of the matter could be represented by knots, and different atoms would be represented by different type of knots. And so they were discussing this, and then they asked Tate to investigate the topic, and he was the first one, or among the first one, to start to make tables of knots and order these knots using, for example, some simple crossing numbers. And why they were thinking that atom could be represented by knots, they were inspired by these smoke rings. The smoke rings, you start them and they will travel in principle forever. And this would represent the stability of the knots. And you can do them by simple methods like this one. And then they could imagine, for example, that two rings linked together would represent the sodium atom with a double line of sodium, for example. And this kind of idea were going around, but this has started the science of knots. So how they are classified, the knots? Well, the knots are classified by many, many different methods, but one of the simple methods is just to count the crossings that are needed to represent the knot in 2 dimensions. And the one that Tate used was the minimal number of crossings needed to draw the knot in 2 dimensions. And for doing this is a trefoil knot, the simplest knot that we know. You see that there are many crossings, but 3 of them are not essential. By using what they are called the Rademaster moves, you can change just the configuration without cutting the knots, and then you will come up with a knot with the minimal crossings. And so, for example, this is the trefoil knot. Using the Rademaster move, you cannot convert it to this kind of shape or this one. But this one, you see, you can easily, by moving the crossings, you can easily transform into this. And so this figure here is equivalent to this one. But this is not equivalent with this one. And so this makes 2 different types of knots. So this is what I was using. A more elaborate example, this is the 4-1 knot. You see it here. These 2 knots are equivalent because by moving these loops here in and out, you will go from this configuration to this one and vice versa. And so you can prove that these are 2 equivalent knots. So you could use these minimal numbers of crossing that you need to draw the knot in 2 dimensions as an invariant and a way to classify the knots. Unfortunately, as you can see, as you increase the number of minimal crossings, the number of different knots grows exponentially. And here you have just a graph. At 16 minimal crossings or essential crossing, there is 1 million of different knots. And this was the work of Twistelthwaite, an Englishman, now in the US, that has prepared this table with the different type of knots. So it's not a good invariant. It will not allow you to distinguish between this knot and this knot or this one, but it will allow to distinguish all these knots from this one or from this one and so on and so forth. But it's not a good invariant. These are prime knots, of course, yes. It's the one that you can, yeah, sorry.
So can people prove that these million of knots are they all different?
Yes, this is his work. And he has developed very different type of techniques to prove that he has counted all the different knots, all the different type of knots. Okay. Yes.
Shouldn't there be a different symbol for if you pass above the string or below the string?
Yes, of course. For example, if you would, but if you take this one, for example, and you cut here and you pass it over, then it will immediately convert into a 7-1, you know. So, but this is not allowed for topology. You are not allowed to cut, you see.
No, I'm asking about notation, because in the crossing you showed the string going above and below is the same notation.
Yes.
He wants, he wants to refine your invariant to take into account
because this is
crossing
these are the moves that are allowed because they don't cut the string, so they cannot change the topology. And then you can go, if you take this example here, so these two lines are represent exactly the same knot.
He wants to orient the knot and then count the crossing.
Yes,
level.
this is it can be done, you know, and this, for example, you can assign to each crossing, for example, a sign, and this then gives you what is the width of the knot. But the width of the knot is not is not an invariant that allows you to distinguish all the knots, because there are especially in the very beginning of the table, all these knots have maybe right +1, +2, or 0, but it's not a good invariant in that sense.
So even if you will assign to each crossing its type, is it going above or below? You will not be able to classify all these nodes.
No, separately not.
Mm-hmm.
You will get a number, which is always the same for each type of knot, but it will not be different. You know, when you look into this list, when you look into this list, this might have a right of 1, this one also, this 0, this and so on and so forth. So it's not a unique way of assign, of then distinguish a knot. So there are other ways to search for invariants. So mathematicians know them. There are polynomials. There are different type of polynomials: Alexander polynomial, Jones polynomials, and this homofly system to distinguish a different type of knot. What I will show you today is one which is based on a kind of a physical idea and was originated by Stasiak and also Grossberg at the same time. So take, for example, the 3-1 knot here and put a tube around the line of the knot, describing the trajectory of the knot. And then what you can do is to inflate the knot, the tube diameter, for example, by keeping the length of the tube, of the line constant, until you cannot inflate it anymore because it touches and you cannot inflate it anymore. And what Stasiak and also Grossberg did then was to take the length of the knot, of the string, of the center line of the knot, and divide it by the radius. And you can see that, for example, if I had taken the 4-1 knot, then because it is more, it has more crossings, this diameter will be smaller for a given constant length. And so this ratio could be an invariant of the system. And so now I just want to illustrate this process because it can be done. And so I made a knot on a tube from a bicycle and glue it together very painstakingly because it was not really airtight. And then you can pump it up and do exactly this procedure here. In principle, if my tube would be a perfect tube, then I could then measure the length of the tube, the radius, and then calculate this invariant. So if it doesn't explode, you know, so you see the process of creating this invariant using a tube and pumping it up until it reaches this compact configuration. Yeah. So you can see that you can do it yourself without any... sorry? A little bit more, yes. Well, then it might not be really good for your ears. And, but you see, so don't play too much, but you can have a look to this configuration. And so what...
Sure, you've got a constant radius when you do this blowing up.
Yes, this is constant radius.
How do you ensure it?
This is by the numerical method that they are using. Just to increase the radius and then let them not move until find the the good configurations and so on and so forth. It's just all numerical work.
This process has a mathematical foundation, mathematical definition. So this process has a mathematical definition.
I didn't understand.
He wants
that.
to know if you can prove, for example, there's a unique, this ratio is a
It's
well-defined, unique invariant, is well-defined invariant. But if you start with a knot, there might be two minimums.
Yes, sometimes there are problems like this, but I think they solve out all these problems and they find one configuration.
But
And
also,
so,
if you compare two knots which are topologically equivalent but have a different shape,
Yes.
how can you guarantee that they would go? to
well,
the same?
finally they will go into this shape.
So they would do these movements just spontaneously.
Yes, but this is it is a numerical problem, you know, to do this, let fluctuate the knot to move around and acquire this configuration here, which is.
Okay, so you give them some freedom to move.
I didn't do it. So.
Well, if you pump the.
Yes, you see that.
it
yes.
rearranges as well. Right?
Yes. And so they will go into this configuration. This configuration is called the ideal knot configuration by Stasiak. You see here the different type of knots for 1, 5, 1, and so forth. You have the whole table, and here you see just represented the central line of the 3-1, just to show you how it looks the knot and after this procedure here.
This one seems deficient. There's a hole in the middle.
Yeah, yes, because you cannot
Really?
pump it out more. Yes, because you see if you fix the length of the tube, then you see if you want to pump it up more, you need more length, so which it will not work. You know.
So the number is the number of crossings.
This one is the number of 6. You see.
Can't ride home.
There was some terrorist here. So this is the number of crossings here.
And the small number?
The small number is just a sequential number that is given to certain rules. For example, for the odd, you put first the toroidal one and so forth, and then there are some rules. But there is nothing more significant about this. And so when they took this ratio, you see that this ratio looks different for each type of knot. And so even though maybe of a small quantity, but this is the possibility to create an invariant for the knots. I just present it because it has a nice physical incarnation with this bicycle tube. So now some physical properties of knots, and I will go and show you some hydrodynamics of knot. And the origin why we studied this kind of phenomena is in the following experiment. If you produce by some way DNA knots, which are drawn here schematically with the ideal knot shape, and then you let them go through a gel by the process of electrophoresis, which is depicted here. You apply, you put your solution here with all these different type of knots, and you put it here, and then you apply a negative voltage, a positive one here, and because DNA is negatively charged, it will drift through a gel. A gel, you can imagine, is like a sponge, and then you can also imagine that the more compact knots will go faster than the open one, because they will go through the holes of the gel more quicker than this one. And what it was found out is that when you put a solution mixed with all type of knot, the DNA separates out in different type of knots. You can cut out this position here and then do further analysis and find out that actually this is really the 6-1 knot, this is really the 4-1, and this is really the 3-1, and so forth.
In these experiments, the total length is fixed. So
The total length, yes.
So it's more.
The total length is fixed, and so the higher complexity knots are more compact, And so from the hydrodynamics, you can imagine that it will go quicker to a solution under the action of the electric field. And so
what is the size of those things?
the size of this is about, the total string length is 3.5 micrometers. But you have to imagine that DNA has only 2 nanometers of diameter. So it's a very, very thin wire and very long in this case. So this is this type of knot. And so we went on with Stasiak to study the hydrodynamic of the knots.
How is the knotting in DNA achieved in this case?
Yes, there are different ways to do it. One simple way is to use viruses. The DNA in these viruses are in a linear form, but you can modify the virus so that the DNA will be knotted inside the capsid of the virus, and then you can separate them out.
So the virus will.
It's anyway die. It will die. Yes.
Yes. Okay. But it will not the.
Not the virus itself. Is by the modification that are done on the virus.
Mm-hmm.
The DNA will be completely inside the capsid where it keeps the DNA. It will mix up by thermal fluctuation, and then it will close because it has the property to have 2 sticky ends that are called like this, and then the DNA can be separated out.
So when it mixes up by thermal fluctuations, then it may just knot itself.
Yes,
so
it will knot
itself.
Then it will close by chance. Most of them may be still open, but part of it will close and will be knotted. You take it out, and then you have all sorts of knots produced like this. It's just like you would take a bunch of strings. You just shake them, and if they're sticky end, then they finally will maybe will be knotted. Okay, and if you put them on the gel, then they will separate like this.
Are experimental errors smaller than the size of those discs?
The experimental, you see it here. This is just the width of the.
So,
it's a tenth or 2/10 of a millimeter.
so
plus
for
minus.
instance, what would be chi-squared for this sphere?
It's very difficult, you can see it. This is the width, So this is the. You will have, you see it right here, what it will be the error in the horizontal axis. On the vertical axis, what they took the average crossing number of the knot. So they take the knot, they turn it in all possible position, and they measure how many crossing they observe. And this gives the vertical axis of this knot. This is why this one has a number which is larger than 3, because in some direction you see more than 3 crossings, And you do this, repeat it many times, and then you get out this number here.
This is obviously a good fit. I was just basically asking for the chi-squared number. You don't know that?
No, I mean, it doesn't make really... there is no theory for this, so it is an observation,
Right, so chi-squared is for observation. So just take your arrow bars on horizontal axis and just tell me what chi-squared is.
Yeah, you can do it, but it's not relevant for the...
So 9.1 and 9.2 will have a different average crossing number, yes?
Yes, and they will also travel differently in the gel. Okay.
But how do you distinguish those from other non-crossing knots?
These were just taken out, and then this is a procedure that Stasiak developed. They covered with Rec A, and then they can identify the knots.
So they know they're 9.1 and 9.2?
Yes.
How about the issue of that not every knot is represented here? That's not a problem.
No, because it depends on how you knot them. So some comes.
So they didn't just choose those ones for which it works well?
No. This is all the knots that were in the solution, initial solution. You cannot choose it because it comes from the procedure how you produce the knots.
So why is there no 7.3?
That's what I asked.
Yes, because in this procedure, 7.3 doesn't form.
But
So-
if it's random, then you would think that
Well,
you should follow.
it's not completely random because in the capsid, the DNA is wrapped up like on a spool, you know, and so there are certain knots that are coming out more often than other ones. And this is was one of the application of this experiment to try, by looking at which type of knot that comes out, to try to have clues how the DNA it is right up inside
So
there.
it looks like most are torus knots.
Yeah.
Most are torus knots.
Well, yes,
Or the ones are torus knots, I think.
yes, you have them torus knots, and because the DNA is right up like this, and then you can imagine that this would be the most probable configuration. So, but what is really interesting is that this is a topological quantity, the average crossing number, and this is a physical quantity, and they are linearly related. So we set out to do some experiments with this. So we produced knots in the ideal shape using epoxy resin and these 3D printers, and then we drop them in a column of silicone oil and look at the sedimentation speed and look at different properties. So you can see here an example. This is a 8 or a 7-1 knot that goes down, and you see that it goes down, that it turns. This is just big like this, so it has a string length of 30 centimeters and a diameter of half a centimeter.
Would the Reynolds number be smaller?
In the silicon, here is in water because to show it faster. But in oil, when we did the experiment, the Reynolds number is 0.01, something like this. And then you take different type of knots and you do the plot, and actually what we find out is that this is just the two axes that are just transposed, that when you put the sedimentation speed as a function of the crossing number of the ideal knot, the average crossing, then you find a linear relationship as in DNA. So it looks like when you have a DNA which is fluctuating very thin and goes through a gel, it behaves like these ideal knots when we drop them in oil. This is.
But the aspect ratio must be quite different.
Yes.
You said initially
yes.
that
Here we have a factor of say 100.
yeah.
And in DNA we have 2 nanometers over say 2000. So we have a factor of 1000 or 1500. So yes, it's true.
There are more knots here than on previous plots, but I'm back to my
Yes,
question.
because we construct them.
Right,
you know.
but my question is again, if we would fill the whole thing from knots with 3 crossings all the way to 8 crossings, will the pattern continue?
Yeah, I mean, we couldn't go further.
So they have data, they presented less, or they
No.
they couldn't create?
The problem is with the experiment is that when you come to higher and higher, then you don't have many of them, and so you will not
But
see,
I think
see
the
them.
question is if you would put on this other graph, if you would on that one,
Here,
if you would insert 7.3, would it fit into this general?
7.3,
yeah,
7.4,
yes.
7.5.
I mean,
because
yes.
not all of them are put here, so the
That is
question
the
is why is
question.
that?
well, here you're saying 7.3 is not in here.
Yes.
Yes, it's true. So
Would you expect it to
I
be here, or would you expect it to be somewhere?
I think it will be in just exactly around here. There is no really,
Well, but
but
experiments.
I
Yeah,
don't
we
know
printed it
why
out.
it's not here.
You didn't
I'm
print
sorry.
it
Eh?
out. Is it because you didn't print it out?
Yes, I mean we didn't do it, but but there is no special,
Okay, so that's just the whole of your experimental
Yes.
data. You did
Yes.
not just pick up some of them which were linear or whatever.
No, that makes no sense. We are experimentalists.
I agree.
It seems like it'd be interesting to print out the same list that you saw, or that you looked at with electrophoresis.
Mhm.
So if you print those and do the drop experiment, and then you could compare the
Yes,
two sets of data looking at very
they compare very well. We normalize with the unknot, and they almost overlap. So we get the same slope of the two data sets. I didn't show this here, but we did it in previous experiment. Okay, then the other stuff that you know is that some knots are chiral, some are not chiral. So if you take, for example, the trefoil knot, it has a left and right-handed form. So when you look at it in the mirror, or you cannot overlap them by translation and rotation. And what it is interesting is that if one turns, as we saw before in the movie, then the other will turn in the other direction. Because it's like you would look into the mirror, the experiment. And here you see a right and left-handed trefoil knot, and when they go down, they just turn in opposite direction, as one would expect from symmetry. But this has some a real application because you can imagine that under the action of the gravity, they go down and they turn. And so now you can reverse the question and say, what happens if I turn the nuts? So if I turn the nuts, I should get some force that propels the nuts. And here is the experiment. So yeah, I just took a submarine, replaced the propeller here with a left and right-handed nut because they turn in a different direction, and then you see the submarine just going around. If it goes around, yes, going around, you can steer it by changing the speed. Yeah, I can go forward and backward. You know, this is an application, so-called, of the nuts and of the chirality of the nuts. Okay, so this is the one application of this, what we just saw of the hydrodynamics.
You say if you would put the same chirality, the thing won't go?
No, because they turn in
so it will stay
opposite direction. Yes, I can. If I can control them and change the direction, then it will turn on itself on one direction on the other. So it works like a propeller, exactly. And when you look at the trefoil knot as it's drawn in two dimension, it looks really like three blades of a propeller. And this is exactly what it is. Okay. Now, when it comes to physical properties and the nuts, there are many properties that are important in their use. One is the security, means that when you are coming down from the mountain, the nut doesn't open, so it's the security of the nut. If you fall off the cliff, you want that it doesn't break, so there is a property about the traction, resistance to traction. There are nuts that you want to open after being under tension because you want to release something, so these properties. Or you want a nut that it opens under tension. Imagine you are in a sailing boat, you have attached your mainsail with a rope, it comes a gust of wind, and you want to release the sail, and you cannot because your nut cannot be untied under tension. So according to the application that you have, there are nuts that you can open under tension, there are nuts that you cannot. So you must be careful which nut you are using. And also in this case here, I mean, how many times we were unable to open a nut because there are type of nut that don't open after being under tension. And what we want to do, I want to show now is this part here, the resistance to traction of nuts. And to do this, we are just taking physical nuts, which are the open one. This is a representation done by Piotr Pieransky in Poznan. And then you take a simple wire fishing line, put a knot on it, pull it on it, and then measure at which force it will break. And what is the result of this experiment? It's very interesting. You take the fishing line alone. It is given a 10 kilogram maximum force of tension. And if you do it properly, it will really break only at this force here. If you put a trefoil knot here, you will have a reduction of 40% of the resistance to traction. And so you must be careful what type of knot you are putting on your rope, because this will reduce the resistance to traction. Yes, and this it will also break at the knot. Of course, I will show this problem just later on. And, but this is one of the problems when you put a knot on a fishing line. And so now the question is to, I can do the experiment right here, you know, just to convince you that, so I have a fishing line. It was really difficult to find a fishing line because nowadays there are only high-tech fishing line around which don't really, you know.
You can't break a fishing line with your arms.
Yeah. So this is a fishing line, so I put a knot on it, and then I pulling is just in the middle, maybe for being sure that you see the knot. Okay, and then when I pull, well, it breaks exactly at the knot. So for a mathematician, this is really not a problem because this is a line and the knot is one singular point. So where should the line break? Well, at the knot. There are no choices to do it elsewhere. You know, I mean, it's a kind of, you know, argument like this. And if I would have measured the force of this, then it would have come out, because this line is about 10 kilograms, it would have come out that at 6 kilograms it will break. But as I said to you, it will depend on the type of knot. And so what we did in honor to London 2012, we did the Olympic Games for knots. And so how goes the Olympics game for knots? Well, you see it here. You put two knots on the same line, and then you pull, and then you look where it breaks. And so now I will redo it. So I will put a trefoil knot on this side here, and a figure 8 knot here. So the 4-1 on this side here.
Do you ask us to predict the experiment?
And what are you asking?
Do you ask us to predict where it will break or not?
No. But you can. You can if you want. So you see the trefoil knot is on your right, and the 4-1, the figure 8 is on your left. And now I'm pulling, and then.
Should we get?
So the one for the 3-1 that breaks the 3-1.
Who bets on trefoil?
On trefoil. Okay.
Break, trefoil breaks.
They have 4, 5, and the figure 8.
Bets on figure 8.
The other guys. So you are winning. So please put your bet. We are in UK where betting is really a national sport.
Winners pays lunch.
Yes, I will pay you a spaghetti lunch. You will see afterwards why. So now I'm pulling. You see, pulling, and where it breaks, trefoil knots. So the 4-1 is stronger than the 3-1, and so the second part, the second people that voted are the winning, and they will get
first.
Sorry. Yes, it breaks. Sorry. Yes, it was not the. You know, I was thinking in terms of strong. You know, winning minority, exactly. And so you will get a spaghetti dinner from me. And then we did this for all type of knot. And so we played each knot against the other, and then we came up with a classification like this. So the weakest one is the 3-1, and as the complexity increases, also the resistance will increase. And the 4-1, you see it is way down this list here, is one of the strongest knot. This is also the reason why when you are doing climbing and you attach yourself to the rope, you do a figure 8 knot exactly at this place here, and it is used everywhere when you need really a solid knot. But the question is, why the string breaks at the knot? Apart from the singularity argument, this is the next question that we try to answer. So these are picture taking of fishing line after the breaking. And of course, it doesn't really tell you exactly what happened at the moment it broke. And so what we did, we took a high-speed camera, 1,000 pictures per second, and made a movie of the moment where the knot breaks. Unfortunately, because of the very high tension and the high speed of sound in the fishing line, in 1 millisecond, the knot is broken and you don't see anything. So the frame before, the knot is intact, and the frame after is broken. So there are no ideas, no clues why it broke. And then we discussed this among different people, and we come up with the idea of spaghetti. This was Piotr Pieransky in Poznan and Sandor Kazas. I hope that Piotr is looking at this talk in Poznan over the internet. And then we did the experiment. Why? Well, in the spaghetti, they are soft, the speed of sound is low, and then the rupture also will occur slower than in the nylon. And so now I will, and this is now we know why you will get a spaghetti supper from me. So I brought here some spaghettis, you know, and you can do the experiment. So you take the spaghetti, you put the knot on it, and then I will gently pull on it, and it will break at the position of the knot. And I can also do the other experiment to put the trefoil knot on your right, on your right, and the 4-1 knot, the figure 8 knot on your left, and then hopefully it will work out as it was before. So be careful of the splashes of olive oil, which is on the spaghetti. So now we'll put slightly, and you see the 3-1 will break before the 4-1. So the 4-1 is really strong. And now we went on with this experiment. So we took this high-speed camera and made a movie of the 3-1 knot. You see it here. And just observe this spot here. It will break exactly at this position here. If we take the 4-1 knot, now it is on the other side of the knot is here. Look at this place here, and it will break exactly at that position. So now we have at least an idea where it breaks, and the reasons for this is that there are two main reasons. One is that the string entering the knot is bent, and so imagine in the case where it's well lubricated the knot, the tension along the string is all the same, but it is bent, so there is an extension out here, a compression inside here, and so this will reach the breaking point before the inner part, and it will start to break here, and the rupture will go into the knot. And so Piotr Pieransky did a numerical simulation with his Sono algorithm. He just made tight knots, and then he measured the curvature. And you see that at the entrance of the knot, there is a peak in both knots here, in the 4-1 and the 3-1. And when you compare them, one over the other, you see that the 3-1 knot has a higher curvature than the 4-1. And so in this case, there will be then more extension in the 3-1 than in the 4-1.
Why is it so noisy? I mean, if you think about this ideal knots, then I would expect that
this is a simulation.
Numerical.
There is a numerical simulation with a given model of spheres
but if you would do the same with a tube, with a bicycle tube, then you will get some smooth curve, right?
Actually, it's much worse. Analytically, you can prove it's discontinuous. Théorique is very
The
discontinuous.
curvature, yes. Why is that? I mean, cannot you just take a bicycle pump and
I mean, the model is not really the bicycle tube. The model that Pieransky's thing approximates is really this excluded tube of unit thickness and you minimize length. It turns out that the curvature tends to jump.
Yeah. And so this is one of the reasons. The other reason, as you could observe, the entering string is strangled by one of the loop. And so if you reduce the section and keep the tension constant, then the stress is higher here than outside. And so there is one reason more because it will break, why it should break at the entrance of the knot. So we published this in 10 years ago now.
The spaghetti photographs, some people are mumbling that too. It looks like it's at the strangling part where
And
the strangling part rather than the high curvature part where the spaghetti.
yes, if you are looking closer, it's now, you don't see it, but it will start to break on this side.
Strangling of these is very easy.
So this side here is the side where the extension take place. On the other side is the compression, and I mean it's difficult to see it.
It's not a very good strand.
But it starts to break on this side. You know, it goes into the knot. But I mean, we can maybe make more experiment. I cook more spaghetti and then. Okay.
Need to try other pasta.
Yes, other shape of pasta. Yes, but this problem was already treated earlier by Saita et al. On polymers, because if you have a polymer, synthetic polymer, it might have knots on the polymer itself, and if you put this polymer under tension, the knots will reduce the resistance to traction. And they did a molecular dynamics simulation, and they found out exactly the same of what Pieransky found. And also when they, here in this color scale here, they have indicated the elastic energy. You see that here at the entrance of the knot, there is more elastic energy stored into the system than elsewhere. So this part here is under tension with respect to the rest of the polymer. And so I suppose that if you take a normal polymer, you pull on it the same way, it will break exactly at this point here. Okay, so now we go over to knots in biology. You know that there are knots in proteins, but this will not be today's talk. I will speak about knots on DNA. You know that DNA is organized over large length scale, about 3 decades. It goes from the 2 nanometer original string. It will be wired up in a very, very complex way to form at the end the chromosome. And now you can imagine that if you are trying to duplicate a chromosome during the division, like you observe here, you see the duplication of the chromosomes, and then the separation of the 2 sets of chromosome in the 2 daughter cell that will take right now place, then you can imagine that there are a lot of crossings, a lot of knots. And the cell has to take care of this problem. To do this, it has special enzymes that are called topoisomerases, and these topoisomerases can change the topology of DNA. There are different types of topoisomerases that can do work in different ways. What I will speak today is Topo2 that was found in Wang's lab. It is an enzyme that takes one string of DNA, fix it in the enzyme itself. It takes a second one, it open it, and passes through the red one will open and passes the green one through the enzyme, and then it closes again. So with this, you have a tool that allows you to open the DNA, pass it over another DNA string and close it. And with this, you can change the topology of the DNA. So it can do topological transformations. For example, you take 2 linked circles and can transform into disjoint circles, or you can take a trefoil knot, transform it in an unknot, and they have also other function in the system. So what is interesting from the point of view is that nothing changes the statistical properties of the DNA, so it will exclude it will increase the excluded volume in the polymer, and so they were very much studied by statistical physicists. So what we are doing is just to use the atomic force microscope, and it's you see it's a nanometer size, micrometer size tip, and you just scan over the surface. And as you can scan over the surface, with the stick, like a blind person uses the stick to walk around, you can get the topography of the surface. And so if we depose DNA on the surface, then we can make a picture of the DNA which is deposited on the surface. And so we did this for knots. Here you see DNA knots similarly prepared like the one I showed you with the gel electrophoresis. And you see the trace of the molecule is about 3.5 micrometer long. And you see that here there are crossings that indicates you that this DNA, it is knotted. So, no, unfortunately, we cannot resolve this. We have now a new instrument, and we hope that we can do it with this, because if we can do this, then we can tell which type is this knot here. And so it will give us information about the question that we had before, which type of knot are in there, and so how it comes and how is the DNA organized inside the viruses. And so you see, always these are more complex knots. You see that all the crossings are all concentrated in a spot. Okay. What we did also was to take a DNA, a knotted DNA, and then add to this solution, while we are doing the images, these topoisomerases that can undo the knots. And you can see it. You can see it now here. These are two knots that are one nearby the other one. And now we start the imaging of the DNA while we're adding topoisomerase. And you see how the topoisomerase has opened the knot. Because the conditions are such that when the DNA has no knots on it, it will just lay down very well on the surface. It will spread out in a two-dimensional shape. And so it's very quick, because it takes us more than 1 minute to do each image, so we are not really fast. You don't see the topoisomerase coming because it's too small. We don't have enough resolution. And the broken line here comes from the fact that we need that the DNA is not strongly bound to the surface in order for the topoisomerase to act on the DNA. Because if it's strongly absorbed, then our picture will be like the one before. They will be very sharp, but the topoisomerase cannot work on it. And so here we were bound by the fact that the DNA has to be able to move so that topoisomerase can move. But you see it clearly how the DNA spreads out once the topoisomerase has acted on the DNA. Okay.
There's only one part of the process you showed before where it was then rejoined again.
Yes, this is topoisomerase comes, finds two crossings like this, opens one, passes the string, the one line through, and closes it again. So here the curve is really is again closed. It's just that we cannot imaging because it's moving around. It's not fixed on the surface. And this is why I was saying this. So if we would change right now the condition of solution, then it will lie down perfectly like the one you saw before. It's not broken in this case. And so the question now is to ask, but how does the topoisomerase, which crossings to pass and which not to pass? Because if you have a mass like this, and then you start to pass one crossing across the other one, you could knot the molecule, you know? And the answer is probably in the following observation, is that because of entropic arguments, the crossings, the essential crossing, at least in 2 dimensions, will localize in a very well, like you see here. It was shown by different works on this subject. And so what the topoisomerase has to do is that if it finds a crossing of DNA, then it must be an essential one, because otherwise it doesn't cross the molecule. And so in this way, by this knot localization, you increase the probability that the topoisomerase finds an essential crossing, and when you just pass it, then it will unknot the DNA. And our observation has clearly shown that the crossings, at least in 2 dimensions, are localized here. So this is one argument that we can bring to this discussion about how does the topoisomerase 2 know which strand to pass to which one. Okay. Now I will, I think, stop here. I just wanted to thank the people that have collaborated with me over the year on these problems, and thank you for the attention.
Questions?
So actually, about a month and a half ago, Dorothy Buck gave a talk out at CanTP where the issue of the rate of topoisomerase affecting crossing changes and so on was brought up. Do you know about, you thought about trying to use these sort of entropic considerations and sort of the rate at which the knotting occurs? I mean, obviously there's some time constants in there, but just if you could rescale those time constants, just using probably that it goes from something either higher energy, lower energy. So it seems like a macroscopic, these nice macroscopic experiments, you could try making some system that does that.
Yes, maybe, but I cannot tell you right now about this. But because there are also questions, for example, that this is one argument that uses Stasiak about the fact that topoisomerase has some preferences for certain type of crossing with a certain angle, that it recognizes this. And then if you produce knots and you see that these essential crossings, they have certain properties. They will cross with a certain angle, and so this could be one way how the topoisomerase recognizes an essential crossing and then will open it and not the molecule.
So essential crossing is the one that really controls if the thing as a whole is knotted.
Yes, yes.
And the problem is that the topoisomerase should find it and uncross it, right? But not do the other ones which are just accidental.
Yes, because you could knot it, if you.
And this entropy argument is that it's entropically good for the molecule to have a large loop.
A large loop and all the crossings in one place. Since the DNA is very thin, it uses very little bending energy, so you can put it in there and you gain a lot because
a lot of conformational
conformational freedom, and so all the crossings are in one spot.
So you mentioned that the DNA is negatively charged.
Yes.
So do electrostatic forces play a role here?
No, there are no. I don't think there are. For example, sequence-specific places where the topoisomerase would come and then unknot the DNA. But for example, of course, if you take topoisomerase as regions which have the opposite charge, so they're positively charged mostly, so that it is attractive to the DNA. But there are these kind of interactions.
Yeah, I mean also the way the shape these knots take.
The shape.
Well, you mentioned that the knottedness is kind of concentrated in a rather small part of the overall DNA, so that this could be due to the DNA trying to blow
because of electrostatic repulsion. Yes, but usually the knots are in 0.1 molar NaCl, so it will screen out almost completely the charges. So the screening length is just 1 nanometer or something like this, 0.1 millimolar. So on the overall shape, it doesn't play a role, but it has an influence on the stiffness of the DNA. So if you want to calculate the persistence length, then this will be influenced by the charges. Yes.
When you say the thermodynamic argument localizes the crossings,
Yeah.
you're meaning the essential crossings.
Yes, because the other one can be undone. We recently with Andrzej Stasiak, we look into another mechanism that could localize the knot, namely supercoiling. You see, you can put turns on the DNA molecule and produce supercoiling. And what happens is that this supercoiling that you see here pushes the knot on one end. And so it localizes the knot somewhere. And then, I mean, this is now an hypothesis that we can test. We can produce knots with different degree of supercoiling and see if topoisomerase 2 unknots them quicker than the one that don't have.
Can you do this physically? If you knot like a foam, I mean, you knot something with torsion, you torque it up.
Yes, yes.
Then it actually pushes the crossing.
Yes, but then, I mean, there are these experiments by Ben Naim who uses chains like this one, you know, and vibrates them. Then you can show this kind of phenomena.
That's the thermodynamic argument.
Yes, then you can, you know, these are the experiments that he's making with chains. I don't have time to show it to you, but you can then make this kind of simulations, you know. You can even do the Olympics here, you know, for example, to see which knot diffuses faster along a chain. You see here you see it's an open knot, and you see that finally it will unknot. So the knot is just flowing out of the chain, so it will diffuse along the chain.
Yeah, it's the same. When you try to knot a snake, it's the same thing.
Yes. I mean,
yeah, you've done the experiment.
You can do, for example, an experiment like this one, you know. You put the 4-1 knot here and the 3-1 knot here. And then you shake it. We could do the experiment right now. So I measure now the distance to have the relative speed of the two. And then I shake it for a while. And sometimes it even happened that I produce a knot at the end of the string. And after a while, I can look at what is the distance. And you see that this has moved more than this one. You see, just by that amount. So the fusion, for example, of the 3-1 knot is faster than the 4-1. And the 4-1 has 4 crossings where there could be friction. The 3-1 has only 3, and so what one can do, you know, look at these problems here. There was a group at Caltech by Stephen Quake. He made knot on DNA with the optical tweezers, and then he looked at the diffusion of the knots along the chain, for example. So these are
What is the effect of the electrostatic forces on the knot?
in principle, as I said, there is always salt in solution, and this screens the electrical the charges down to 1 nanometer or even less. So there is no, in principle, effect.
Long-range forces.
No long-range forces, yes.
When you do the bicycle tube experiment, I mean the procedure, you have fixed lengths. Well, how does volume change? I mean, what's the relation between volume and knottedness?
Yeah, well, in principle, you have exactly, you know, if each knot has a length to radius, as a length to radius, a fixed length to radius ratio, then the volume is just the length times the square of the radius, and so then you if this is for a given knot, then you can look what does the, you know, the volume. So
it scales like
so the volume reduces as you you know, because the length stays constant and the radius just diminishes. know.
I said no longer, it goes faster through the fluid. Right?
Sorry?
No, if a sphere had this radius, what would be the propagation in the fluid?
Ah, okay. So we did the experiment, and we took a sphere, which has the same volume as our knots, and if I am not wrong, it is about 10 times faster, something like that.
The sphere is?
Yes,
Yeah.
something like this. I cannot tell you that. I
The same
don't.
volume, but the cross-section it
The
presents.
cross section is different.
It presents to the fluid.
Yes,
different.
because if you take, for example, the unknot, it has all this surface here, and.
More questions?
May I ask a question?
Yeah.
So I like to ask the growth rate of the strings. So you said the purple is the weakest one.
Yes.
And so if complexity increase, so the strength or increasing or converts to the some constant.
The strength on traction, yes, probably it will reach some, because the maximum is just 10 kilograms. So there is we cannot go above this.
Yeah, but so it's approximate to the 10 word. So combines to the some lower value. For example, we cannot really measure exactly the rupture force for each knot, so we cannot do this experiment. We just know which one is stronger respect to another one. So this is the only thing we know.
In the job experiment, if you deform the knot drastically, will the result be the same as before?
In which
the job the knots in the water. If you deform
Dropping.
The dropping, yes. If it is deformable.
Yeah. Well, he's wondering how much it depends on the actual shape of the ice.
Yes, of course. You see different type of knot. So the more the knot is compact, the faster it will go. So this you see it clearly. And the other is that if you take flexible knots, and so we are now analyzing this kind of data. We took chains like this one and dropped them into the tank and measure as a function of the knot type what it does, but the behavior is much more complex than what we expected actually.
Because now they can deform.
They can deform while they come down. It's for example, if you take just a string, the string takes a shape like this, something like this, and then sometimes it cumulates here, it starts to cumulate here, and then at the end it's just one blob, So it's really complicated. And our tank is 50 centimeters wide, and so the problem is that when it does, for example, something like this, it goes toward the wall, and then I don't know how much the wall might influence the, what it's doing, but it's really complex. Already with one string, it's really complex. So what is interesting, if you take two links, two unknots linked like this, what they do when you drop them, they try to overlap like this, for example. So it's.
So with time, their speed usually goes up. Yes.
Yes, in this case, yes, because they will just reduce kind of cross-sectional, and so it's really complex stuff now with these flexible strings.
So it does not depend only on the topological aspect.
No. See, it depends on the topological complexity if you keep the material and saying the ideal knot shape, then you get a straight line, But all the rest is really very complex what they do.
So why the experiment in the DNA test?
Yes, this is a question which is really the really puzzling this result. But we also did Monte Carlo simulation of gel electrophoresis, and we got exactly the same results. So we just made a gel by some obstacles, and then put in there nuts with some charge, and then drove them through the gel, and we get out exactly the same dependence. And so what I'm always saying is something like in these terms here, is that if this is a general way, so we have speed here, and here we have the crossing number. And so this would be topology, and this would be physics. Okay, and so the linear relationship tells me that physics is equal topology times a constant. And the constant has units of physics over topology, and this is one question, one remark I always show to people, because you see, as you said, you take a flexible DNA, it behaves exactly the same. We take a rigid one, it behaves exactly the same. We can do whatever we want, the simulation with Monte Carlo, we get always this relationship here. And so it is rather interesting for me if one could calculate this constant here.
Clearly less than one.
Sorry?
It's Planck's constant, isn't it?
It's clearly less than one.
Yeah. Yes, but you see it's so there were Gonzalez and Maddox did exact calculation in the limit of Stokes flow for all this shape, and they get out this behavior. But somehow, what is intriguing for me is this general.
I think you have to normalize physics.
by the four-dimensional space, something like this, with the topology of the space.
Measure of physics is velocity. You have to normalize it with some.
And what would be the units for K? Another question.
Yeah, well, in this case, it's meter over seconds.
Yeah, but you say in general physics.
Yes.
Normalize it with velocity.
Is topology dimensionless?
Sphere of the same volume.
It's Nobel Prizes over
It
field
should be.
studies.
Then physics is okay with the units of physics.
Okay, I think we're competing with the other program for lunch.
Yeah.
So this is serious. It's like 2 knots going down.
But if you get spaghetti,
Two vortex.
I mean, what they can offer to you.
This is all we got.
That's leapfrog then, right?
They can offer you spaghetti.